Hello, folks. Today we're going to talk about node selection when it comes to making transactions. So in Zcash is based on UTXOs, just like Bitcoin. So any of these cryptocurrencies have the challenge, or they need to, when they form a transaction, they need to select inputs and outputs. What does it mean? It means that when you have a transaction, you create new outputs, like the bills and the notes that you have in the coins that you have in your wallet. They are going to be separated denominations. So if you pay somebody 3x, he's going to receive a note, a virtual note of value 3. So in our example here, I have inputs. We have different nodes. The nodes in red are going to be the nodes associated to transparent addresses, and the nodes in blue are shielded. So let's start with putting them aside, and we can ignore them for the moment. Right, so we have 5, 1. So we assume that we have received in the past 5 ZEC and 1 ZEC and 2 ZECs. We have 3 nodes of these values. I'm going to align. And let's say we want to pay somebody 3 ZECs. So, for the beginning, we want to pay them. They provide a transparent address. So these 3 ZECs here. Transparent ZECs. So that's what they want. And how do we make a transaction? So we know that the output would be 3 ZECs for them. And we can do that by adding either 1 and 2 in our inputs. So 1 plus 2 equals 3, so that's perfect. Or we can also do 5. But if we do 5, then there's a change, right? So 5 is too much. So we have a change of 2. And the change would be sent back to us. So this would be assigned to the address of the receiver, and this one will be sent to our own address. But it's pretty much the same. In one case, we have 2 inputs and 1 output, and in this case, we have 1 input and 2 outputs. So, and when we pay the fee, transaction fee, currently we don't really care about the size or the number of inputs and outputs. So we would pay the same. And by the way, in the rest, I will ignore transaction fees. So normally you would have to pay a little bit more. So 5, 3, and 2 is exactly balanced here, and you are not paying anybody. So we should be paying a minimum fee 0.01 millisec to the miner. But let's forget about this for the moment. Okay, so this is this very simple case where we have we are paying somebody on 3 ZEC on a transparent address. Let's now consider what happens if if that person wants to be paid in a shielded address. So instead of these 3 red, now we have a 3 blue. So nothing really changes because we don't have any nodes that are shielded. All we have are transparent nodes. So yeah, we could do the same. Let's say we do this 1 plus 2. When we do a transaction like this, we are actually obviously going to reveal our transparent nodes because they are transparent. And we are also going to reveal that the sapling receiver is getting 3 ZECs into the pool. So what it means is that, oh, there's an ambulance going by, very loud. Sorry about that. So in the transaction, whatever you have shielded on, the left and the right. So the left is input and right is output. The difference between the right side and the left side is going to be public in the transaction. So in this case, we have 3 Zex and sapling on the right, and 0 sapling on the left. So this is assaying something like this. So as if we have this, and in which case the transaction will have +3. It will indicate that we have 3 Zex that went into the sapling. Right? So this is what we call a D to Z transaction, because we went from transparent coins to Z coins. Now, let's say what happens if we are paying somebody, and we already have some nodes that are shielded. So let's say we give ourselves, we turn these 2 into 2 Zex, but shielded. Let me change the color. Now this is shielded, and if I pay, so I use 2 shielded and 1 non-shielded, non-transparent. In this case, this guy is gone. All right, so I still can pay, still works. But now we can see that the transactions will say, and the net change in the sapling pool is only +1. So this information here, we will not see 2 and 3, but we will see the difference between these two values. We would have in the transaction, we would have +1, right? 3. So let me see, I can write it down somewhere. Easier if I copy paste actually. Right. So you will say +1. So that information is in clear in the transaction, as well as this one here. So everything in red it will be in clear, and this guy will be in clear. So this is what happens if you do a sampling transaction that has some shielded and some unshielded. There's, you can see that it's revealing more information than now if we had everything shielded. If we go everything shielded, we consider this one is down shielded as well. Right? In this case, now we have 3 output and 3 input. So now this guy is going to become 0. Right? And of course, if we see 0, it doesn't say anything about the values there in there. So this is a full shielded transaction, Z to Z. And finally, you have the case where you would have shielded inputs. So and then you want to have a transparent output. So this guy here is transparent. So in which case, this is the opposite. We have 3 as an input, but 0 as an output. So that means that our net change is -3. You can see that also in the transaction. So that information plus this information, of course, are going to be public. In the best case for us is if our transaction is shielded to shielded without any transparent component, because then we will just have a 0 here, which doesn't tell anybody anything about the amount that was transferred. So it's pretty simple if we had only transparent and shielded nodes. But now now we have Orchard. Right? Orchard is a second type of shielded address, shielded coins. So let's mark them as green or different color. Let's mark them as green. So let's see. Let's say that instead of having 1 and 2, this guy here, the 2, is is gonna be color, right? Be a good color. Is gonna be orchard. Right? So what's gonna happen if this is orchard? Right. So if this is orchard, and I do 1, 2, and 3, we are going to have a net change in the blue pool and the green pool as two different values. So of course the red value is always in clear, so everything is shown for them. The value themselves is shown. Whereas for the blue and the green, only the difference between inputs, outputs, and inputs is shown in the blockchain. So in this case here, because we have 0 on the output side, this is going to show -1, right? And this is going to show is also 0. This is going to show -2. And finally, we have a 3. So now you can see that because we have nodes are different pool, we're actually revealing way more information than before, because we're revealing that we have taken money from funds from the sapling pool of value -1 and funds from the orchard pool of value -2. So our transaction is not as private as it was before. And even if you are considering doing a shielded to shielded transaction, so now let's say you are paying somebody not on the 3, but you're still paying 3, but not on the 3 transparent, but the 3 shielded. Okay, so now we're saying that this person wants to be paid 3. So now this person wants to be paid 3, but 3, let's say 3 in sapling, in the Z address sapling. So I'm going to change this to blue. Right, so let's move this guy out and say that this out. This is 3. Right, so we want to be paid 3. It shows that this guy has to be -2. Right, sorry, +2. And now we can see that because our wallet didn't have enough to pay that person in the sapling pool, we are revealing that the transaction has involved 2 ZEC from the orchard. So these value here are shown on the blockchain, and therefore it's not as secure as it was if it was on the same pool. So you can see that the situation is a bit more complicated when we have recipients which accept a certain type of shielded funds, but not the funds that we necessarily have. So when we talk about shielded addresses, we have now to make a distinction between shielded orchard or shielded sapling. They are not fungible directly. So you can see that even though what I mean is that even if you are doing a transaction that is Z to Z, so a fully shielded transaction, it is still revealing something. And the situation becomes harder and harder if you have multiple recipients. So if you have somebody who also wants to have, so we have 2 recipients, right? If you want somebody who also wants to receive, let's say in this case, you want to receive 2 here, 2 here, and then 1 here. So same total. Now, when we pick these nodes, we may want to pick in a way that minimizes the knowledge exposed, revealed. If we had two here and 1 here, so I have 2 1 here, then that would bring a 0 to this net value. We would reveal that we use 1 orchard. Right? So this is better than if we were doing the opposite. If we were doing 2 here and 1 here. Right? So if we do this, the result is the same, but this reveals 1 and this reveals -2. So it really depends on what you have as inputs in your pool, and also remember that even if you have a total of 5, it could be that you had 5, but as separate nodes. You have 5 as 2 and 3. You cannot you cannot use 4. You have to use either 2, 3, or both of them together. They are not splittable. It's all or nothing here. So the choice of nodes that you have here may not be as perfect as you want, because maybe you want to have 2 and you have more than 2. So let's say that you actually have, let's say you have 1 and you have 1 and 3. So you have more than enough to cover the 2 here. But unfortunately, you can't do 2 exactly. You have to use 3. Right? So in this case, you will use the node of value 3, and then you will have to reveal -3 here. So that's the case, that's the situation when you have several inputs that are of different types and several outputs, so several payers, recipients that want money, that want fund in different kinds of addresses. Now you can get even further, even more complicated with unify addresses. So far, we have been dealing with addresses that, for the output side, that are of one particular type. So if this person wanted 2 on 2 6 on the sapling, he wanted on the sapling address and only in the sapling address. This one is 1 ZEG on the transparent address and only on that transparent address. But now with unified addresses, you are giving the recipient is giving the algorithm, giving the wallet, the option to pick which address he finds more convenient. So in this case, let's say that we are combining. We are not saying now that it's 2 blue, but we are saying it's 2. Let's say between blue, let's say turquoise, cyan. So it's 2 cyan. 2 cyan is a strange beast, because what it means is that the wallet can decide whether to pay in the sapling, as a sapling or as an orchard. So let's go back to our keys here and see what we can do. So we can see that we have a node of 1 and a node of 3. These are not biased. Let's see with 2 here, right? The most optimal way to do this would be actually to say to not use sapling, because if we use sapling for this output, we don't have enough, and then we have to reveal. So let's clear this guy for the moment. Don't know what we have. So we put 0 question mark for the moment. Don't know what I'm going to use for this. All right, so what should I do? I think that what makes more sense is to say that this recipient is okay receiving in orchard. So in that case, I will turn this guy back into green to indicate that orchard is okay. So now orchard is okay, so I will put orchard here. And that means that this guy has no sapling. So sapling. All right. So now we have this combination, and we are revealing 0 on orchard and revealing -1. So we are just revealing the stuff that we already know that we had to reveal because we're using a transparent output here. All right. So that's the idea. The idea is that when you have orchard receivers are no longer just by themselves. Well, they are part of unified addresses, and unified addresses can give the wallet the option to pay in different addresses because they combine different addresses together. So a UA can be just like one address type. It could be a UA that just wraps sapling, but more likely it's going to be an address that wraps orchard and sapling, which means that the wallet can either decide to pay on the orchard address, sub address, or orchard receiver, sorry, or pay on the sapling receiver that are both included inside this unified address. So this is a case where, well, it seems logical because we have two orchard, but sometimes it's the opposite. Right? We had two orchard, two sapling and one orchard, and likewise our recipient uses a unified address, a UA, the sign address. In this case, it is beneficial for us to turn that two cyan into a two blue, make it a sapling address. And now this guy here is orchard, and we have 0, 0, and -1. If instead, again, if instead we made the kind of like the suboptimal choice of using our option as orchard, right? So remember, this guy was either sapling or orchard, but we say, oh, our wallet can do orchard, so let's do orchard for everyone. If we do that, right, and we turn this guy into orchard, this guy here, this guy here, now this guy here, you can see that this reveals -2, and this reveals 1. All right, so we reveal more. So the end result is always the same. The end was always going to be 0. But the distribution of the values here is going to be impacted by which choice you make when you pick up nodes. And for smart wallet, we want that choice to be as less revealing as possible. So we basically want these numbers to be as small as possible. So in the proposal for Y wallet smart node selection, we want to design an algorithm that chooses these nodes in the most optimal way, including for cases where you have multiple receivers in the UA, multiple recipients because it's a multi-payment address, and you have also multiple sources of funds because you have a wallet that is transparent, sapling, and orchard. So combining all these cases together, multiple input sources, multiple output destinations, plus multiple options for destinations, it makes the problem fairly complicated. Especially if you want to have an algorithm that is both fast and optimal when it comes to keeping preserving your privacy.